Pre-statistics. Piecewise functions. Lesson objectives. Evaluate a piecewise function. Determine the domain of a piecewise function. Lesson objective. Definition. When functions are defined by more than one equation, they are called piecewise defined functions, or in short, piecewise functions. So as we see with this wordplay, these are different functions that are pieced together. They are defined differently on different parts of the domain. We can think of the absolute value function as a piecewise function. It is given by this formula. Y is equal to f of x, which equals the absolute value of x, which can be pieced together by a positive x when x is greater than or equal to 0, and a negative x when x is less than 0. So this part of the equation tells the viewer what function to use within this domain. The graph of an absolute value function looks like this. So when x is 0 or a positive number, we use this graph, which is x has a slope of 1, y-intercept of 0, and when our domain is less than 0 or negative numbers, we use negative x, which has a slope of negative 1 and a y-intercept of 0. Example 1, f of x equals 2x plus 1 for x is less than 4, and 4x minus 10 when x is greater than or equal to 4. We want to evaluate these numbers. Solution. So when x is 0, we want to find what is the value of the function. So when x is 0, this tells me to use this function because 0 is less than 4, so I use this part of the function. Negative 2x plus 1. So I say negative 2 times 0 plus 1. Negative 2 times 0 is 0 plus 1 equals 1. So f of 0 equals 1. When x is 3, 3 is less than 4, so I'm still going to use this part. So this will be negative 2 times 3 plus 1, which gives me negative 2 times 3 is negative 6 plus 1, which is equal to a negative 5. So f of 3 equals negative 5. F of 4, x is 4, so we don't use this one. 4 is greater than or equal to 4, that's true. So now we use this one, this piece of the function. So this now becomes 4x, which x is 4. So 4 times 4 minus 10. We multiply first, that's 16 minus 10. And the answer is 6. So f of 4 equals 6. Finally, f of 6, x is 6. 6 is greater than or equal to 4, so again we use this piece of the function. So this is 4 times 6 minus 10, which is equal to 24 minus 10, which is equal to 14. So f of 6 is 14. Lesson objective. If we are asked to find the domain of a piecewise function, we want to know all the possible x values. So for this graph, the domain would be all numbers from here to here. Now when we're given a equation, we can simply look at how the domain is defined. Here's an example of a piecewise function that is called a step function, and we see that there's a piece here, a piece here, one here on the x-axis, and one here. So again, the reason why this is called a step function is as the domain part changes, the range steps up or down. And if we wanted to find our domain, we can just look at how the piecewise is defined. So this tells us which piece to use given a certain part of the domain. So this is all numbers less than or equal to -2. That's interval A. Interval B would be all x's that are greater than -2 but less than a -1. That would be section B, interval B. When x is greater than or equal to a -1 or less than or equal to 2, we use interval C here. So that would be 2. The next one, when x is greater than 2 and less than or equal to 4, we would use interval D value, which would be 0. And then all numbers greater than 4, that would be in the interval E, we use a 1. So for the domain of this function, this would be all real numbers. And if we notice here, there is not a place where an x can be in two intervals. They have to be what we call mutually exclusive. And the reason why is this would not be a function if that was not the case. For every x, there can only be one and only one y. And if you have an x that are in two pieces, that's going to produce two different y values, and it wouldn't be a function. Let's do an example. Example 2. For the following piecewise defined function, f of x equals x plus 3 if x is greater than or equal to 2 but less than 1. It's equal to 3 if x is equal to 1. And if x is greater than 1, we use the piece -x plus 3. So A, find f of -4, f of -1, f of 1, and f of 3. B, find the domain of f. C, sketch a graph of f. Let's look at A. F of -4. Well, if we look here, this function is only defined when x is greater than or equal to -2. This is smaller than -2. We say that the value does not exist. This is undefined. F of 1 is 3. We see that here. So when x is equal to 1, we use a 3. F of -1 would fall into this region. So we use x plus 3. So that would be -1 plus 3, which is equal to 2. So f of -1 is 2. Then f of 3, 3 is greater than 1, so we use this piece. So this would be -x or -3 plus 3 equals 0. Part B, we can see from how this function is defined, x can equal -2 and x is greater than 1. So in interval notation we have bracket -2 to positive infinity. If we were to write this using inequalities, we say -2, it can equal -2 all the way up to infinity. And that's the same thing as saying x is greater than or equal to -2. So the domain can be written this way, or this way. So all numbers greater than or equal to -2. Part C, so from -2 all the way up to 1, we use the function x plus 3. So when x is -2, we use x plus 3, which gives us 1, which is about here. When x is a -1, we have -1 plus 3, which is positive 2. So when x is a -1, f of x is 2. When x is 0, we can see that this is 3. So the y-intercept's 3. Now when we do f of a positive 1, we no longer use this piece. This piece is only defined till we get close to 1. So we have an open circle here, and when x is equal to 1, the function is defined to be 3, so we put a solid circle at y equals 3. And then for all numbers greater than 1, we use the second piece of the function, which is negative x plus 3, which gives us this bottom piece. And we should add an arrow to this graph to tell the reader that this is going on to infinity. Thanks for watching.